So metal cutting, the first part that we're going to talk about is thermal cutting processes. So thermal cutting is when we use heat to cut material. And so there's two different categories of cuts. So before we even talk about thermal cutting, whether we're talking about thermal cutting, cutting with a saw, cutting with a shear or a grinder, there's two different types of cuts that we do down in the shop. That is primary cutting and secondary cutting. Primary cutting is when we cut stock to our initial overall desired length or shape. So like I talked about in lab last week, we have a long piece of material, typically 20 foot when it comes from the manufacturer, and then we want to cut that to our desired length or shape. We don't always need a 20-foot section. Very rarely do we actually need that, but our primary cutting is the initial cut that we make. Secondary cutting is further processing on that primary cut. So maybe we want to drill a hole in it. Maybe we want to tap some threads in there to thread in a bolt. Maybe we're just deburring that piece of material. Any type of cut such as that would be considered a secondary cut. Now, we refer to these types of cuts in our shop in the university level. You may leave here and never see this definition again, or you may. So this is something to keep in the back of your head. Just what you may hear people call that type of process, okay? So we're going to talk about two thermal cutting processes this semester. The first of those being oxy-fuel cutting, and the second being plasma cutting. So what is oxy-fuel cutting? Oxy-fuel cutting is using an oxy-fuel torch, commonly known as an oxyacetylene torch, but we can use other fuel gases besides acetylene to preheat and cut materials. Okay, so what this gentleman here is holding is an oxyacetylene torch. You can see the cutting tip right there, and he's basically holding a cutting torch, and you're going to use that torch to cut a piece of this flat bar. So how does the oxy-fuel cutting process work? Well, the first thing that we have to do is set our oxygen and acetylene pressures based on the tip diameter. So when you purchase an oxyacetylene tip or cutting torch, it's going to come with a tip. And you can buy other tips that are interchangeable. To know what pressure to set your acetylene and oxygen on, you should refer to the package which it comes with it. That will give you the allowable pressure ranges that you can use. Down in our shop, we use 5 psi of acetylene and 30 psi of oxygen. Use an oxyacetylene regulator, okay? Just like the one pictured here. Can y'all see that? This is an oxyacetylene regulator. So here we have, this happens to be an acetylene regulator, but we have a tank pressure gauge, we have a torch pressure gauge, and we can increase and decrease the pressure of the gas by twisting this knob. Basically what we're doing is compressing a diaphragm in here, and it's pressurizing the gas to our desired pressure. Okay? We'll get into more of how those regulators work and the setups work when we talk about welding. So once we have our pressure set where we want them, the next thing we need to do when we oxy-fuel cut is to light the torch and to preheat the material to its kindling temperature, around 16 to 1800 degrees Fahrenheit, using that flame. And so we need to preheat the material to get it hot enough and get it almost into a molten state. It's going to appear red and bubbly in the way that it looks. Once it gets that bubbly state to it, we can assume that you've reached the kindling temperature of that material. Once you've reached that kindling temperature, here comes the fun part. What we're forming is iron oxides or slag. That's what that red bubbly stuff is called, oxides or slag. Once it's formed, we can mash down the lever on the cutting torch, and what that does is blow out a large stream of oxygen. And that burst of oxygen is going to blow that molten material out of the joint, separating the two pieces of material. So real quick, here's an oxyacetylene torch. We'll set our pressures, set our torch using these two knobs. oxygen and acetylene will run out this nozzle here to the tip. Once that material reaches its red state, the kindling temperature, we will depress this lever here, and when we do that, it will blow the material out of the joint. So when do we use oxy-fuel cutting? We can use oxy-fuel cutting when we cut mild steel. Mild steel is just carbon steel. That's just another word for it. Mild steel tends to be of a lower carbon content, which we'll talk about later this semester. But the steel that we use in the shop basically will describe mild steel. Oxy-fuel cutting does not work well on stainless, and it does not work well on aluminum. It doesn't work well on aluminum just because the flame is so hot and the flame affects the material around it, the cut. Oxy-fuel cutting is typically preferred on thicker materials, greater than a ½ inch. You can cut smaller or thinner materials with it, but you'll have to get a smaller tip to cut that with so you don't produce as much heat. And the size of the material that you can cut depends on the tip diameter, so the size hole in your tip. All right, so moving on. So what do you need to be an oxy-fuel cutter? Okay, so what do we need to do this cutting process? We need an oxy-fuel setup. So we need things such as an oxygen tank and an acetylene tank. We'll need a set of regulators, one for each tank. We'll need all our oxy-fuel safety equipment, which I will cover it during the welding section, things like flashback arresters, and some of the other safety equipment, how you test for leaks, leak detectants, things such as that. Okay. You'll also need safety equipment. You'll need a pair of gloves. You'll need a shade. I normally recommend a shade 5 torch goggle and welding jackets because you're going to have some popping and some spatter that might blow back at you, and we don't want to burn your arms. And you'll also obviously need a cutting torch and a set of tips for that torch. All right, so if we're not using a torch, we're typically going to be using a plasma cutter if we're performing a thermal cutting operation. Torches definitely have their place in industry, but plasma cutters have come on very strong in terms of kind of being a more efficient way of cutting thermally. So a plasma cutter, what a plasma cutter does in layman's terms is it takes compressed air from an air compressor and it takes electricity from an outlet and it combines gas or that compressed air and electrical current, and when those two mix at a high velocity and they're pushed out of a small hole, which we call an orifice, it creates what we call plasma. Plasma is the fourth state of matter and is a very hot stream of gas that we can use to cut metal almost instantaneously. Okay? So the definition of plasma cutter, as it states here on the slide, is the process that shoots out a jet of ionized gas. Ionized gas is just gas that is mixed with an electrical current through an orifice, which is the small hole on the end of the torch. And what that does is it creates a high velocity airstream that is electrically charged that creates plasma. There's also a video on Moodle that says, what is plasma cutting? Take a look at that video at the conclusion of this lecture as well. It's from Miller. Miller is a maker of plasma cutters and welders, and it does a very nice job of explaining what actually is going on with the plasma cutter itself. So how do we plasma cut? Here is the process. I know this is a lot of information. We'll just try to take it in. So the first thing that you should do when you walk up to a plasma cutter is obviously make sure that you have a source of air and that you have a source of electrical current. Once you have that, you need to set the air pressure and the amperage of the machine to what the electrode tip is calling for and for the specified metal thickness that you're cutting. So you may have to adjust the air pressure or the amperage of the machine based on the tip size and the metal thickness that you're cutting. Go ahead at that point and attach your grounding clamp to the material. If you don't attach that grounding clamp, just like with a welder, it cannot complete the electrical circuit and it will not cut. Once the trigger has been depressed on that plasma cutter. Once you have the grounding clamp on, get down on your material and then depress the trigger. Once you depress that trigger, the compressed gas will swirl around in an electrode. Okay, so inside of the plasma torch, there's what we call an air swirl. The air swirl is just a piece of material that has some grooves cut in it, and what that does is make that air pick up velocity as it travels through the torch. Inside of that air swirl is what we call an electrode. The electrode is what conducts the electrical current. So it is what is heating up inside of that torch. So we'll have the electricity in the center and the gas swirling around it, and that is what produces that ionized gas, the heated gas. So the heated gas and the electrical arc are forced through a small hole, which we call the orifice at the end of the torch. As we increase the pressure of that gas, because that orifice is restricting the flow, so it's increasing the pressure within the torch, it creates what we call plasma. So it's an electrically charged gas that is pressurized. Once that gas or that plasma exits the torch, it heats the metal to its ignition temperature or the kindling temperature almost instantaneously. So you do not have to preheat material when you use a plasma cutter. It provides such a dense and intense amount of heat to that cut that you don't have to preheat it no longer. And once you begin your cut, the molten metal is blown out of the joint by the pressure of the gas coming from the nozzle. So in a typical plasma cutter, 20% of the compressed gas is used to become ionized. It gets heated up. The other 70 to 80% of the provided gas from that plasma cutter is used to blow out the joint or blow the molten material out of the way. So when do we want to use a plasma cutter? Plasma cutters are typically preferred on thinner materials, less than a ½ inch, so they work very nice paired with an oxyacetylene torch where we do greater than a ½ inch because of the smaller heat affected zone. So let's discuss what a heat affected zone is. When you heat up a piece of material, it changes the properties of that material. It changes how brittle or how ductile it is, which we'll talk about later on the semester, or how easy it bends or how easy it might break. And that's due to the properties that we're changing in that material due to the heat. A plasma cutter focuses the heat on the cut in a very small area. So it has a very intensified heat, but it's only in a small area. An oxyacetylene torch, it has a large heat affected zone, meaning that it affects the properties of that material way past where you cut at. That's not always preferred. So when you don't want that type of heat affected zone, you're definitely better off going with a plasma cutter. Plasma cutters can cut materials greater than a ½ inch. Some materials can cut, or some plasma cutters can cut material greater than an inch in one single pass. You can also use a plasma cutter when you cut ferrous and non-ferrous materials. So plasma cutters are used to cut aluminum, stainless, and cast iron. They're typically preferred on aluminums because they have that less heat affected zone. Aluminum has a lower melting temperature, meaning that it tends to melt rather quickly compared to steel. And so when you try to cut that with an oxyacetylene torch, it just kind of turns into mush. It doesn't do very well. Plasma cutters you can use to cut aluminum. We can also cut stacked or expanded materials with a plasma cutter. So we can stack multiple pieces on top of each other, and we can cut our expanded sheets with those devices. The last thing that I want you guys to be aware of when using a plasma cutter is the width of the cut, or what we call the kerf. The width of your cut depends on how fast or slow you move that torch across the material. If you don't want to have very much burn back or melt back from your cut, you need to move rapidly across that cut. So take your torch and drag it quickly across that material. The slower you cut, the larger the kerf, or the wider the material is going to melt back from that cut because of heat buildup. So I typically tell students the correct speed to use a plasma cutter, and I'll mention this also in lab 2, is when you go to cut, the spark should go towards your feet. So when you're cutting, the sparks will blow down towards your feet and you're going at the right speed. If they blow back towards your face, you're going too fast. You need to slow down a little bit. But while they're going towards your feet, make sure you're not going so slow that you're melting a lot of material back as well. You just want to go long enough to melt through that entire piece of material and steadily move that torch. So what do you need to be a plasma cutter or to do plasma cutting? You need a plasma cutter apparatus. This is basically just an electrical device. They're rather affordable nowadays. You can purchase one and you can cut all sorts of materials with it. You also need a source of compressed air and electrical connection or electrical current. You'll still need a pair of Shade 5 goggles. You'll need a pair of gloves and a welding jacket because it will blow back sparks towards your body. You'll also need consumables for torch handles. So your air swirl, the electrode, and the drag tip on the outside will wear out over time. A lot of these newer machines will throw a code telling you that which piece needs to be replaced. But it's always a good idea to have those consumables on hand in case you need to quickly replace them.